Welcome back, everybody. The topic this week is to give you first a quick reminder on the VQE method and also how we're going to simulate these different Hamiltonian systems and why we end up with the procedure which we have. So the basic things which we're going to go through are some of the elements in the project, where we start with this 2x2 matrix, which we can model as a one-qubit system. And then we are going to see examples on how we can model a two-qubit system and how we can actually build up our own codes for this. The thing I wanted to remind you a little bit about is also the lectures from last week and the week before. So if you go back to the lectures from last week, and let's try to do that. So that shouldn't be that one. And so let's just bring this up. So when we, last week, we went through the setup of the Lipkin model in terms of Pauli spin matrices. So the topic is to try to solve this model here, which we, the week before again, on the week of March 13 to 17, we rewrote in terms of these so-called quasi-spin operators. So you don't need to think so much about this, but the important thing when we are going to run quantum computing calculations, in addition to the energies being expectation values of different measurements, we need to rewrite, in order to have a practical algorithm, we need to rewrite a given Hamiltonian in terms of a Pauli X, Pauli Y, and Pauli Z matrices. And if you go down the slides from last week, and the week before, we saw how we could set up this problem for a case with a total angular momentum or total spin equal to 1, or total spin equal to 2. And these are the two cases which we will look at in the project here. And for one of these, we end up with a 3x3 matrix, which when we transform this into Pauli matrices is going to be represented by a two-qubit system, which is a 4x4 matrix. We're going to skip some of these things, but the thing which is interesting for us now is how we can rewrite this expression which we had in terms of Pauli spin matrices. So I have added to the lectures which we had last week some of these mathematical details. So we can now we can rewrite this in terms of the one-body operators using second quantization, which means that, and this is partly a repeat from what we had last time, we can rewrite the Hamiltonian in terms of these quasi-spin operators, which in turn can be written out in terms of Pauli X, Y, and Z matrices. So what we end up doing then is to rewrite this single particle operator, which previously was written in terms of second quantization operators, in terms of the Pauli X, the Pauli Y, and the Pauli Z matrices. And that means that we can rewrite our Hamiltonian in terms of a set of Pauli Z matrices and the product of two Pauli X matrices and two Pauli Y matrices. And when we act on a given state, so when we have this XX, YY acting on this state here, we end up with a 1, 1. And similarly, we end up with a 0 when we act on the 0, 1 state and the 1, 0 state. And similarly, we end up with the 0, 0 state. So these are just examples. Now, when we are going to implement this, we cannot write this as a product of two Pauli matrices, Pauli X and Pauli Y matrices. And the reason for that is that the computational basis which we are using, 0 and 1, are not eigenstates of the Pauli X and the Pauli Y matrices, but they are eigenstates of the Pauli Z matrices. So this is something which is important to keep in mind. The equation which you have here leads to a rewrite of the spin equal 1 case, which resulted when we diagonalize it in a 3x3 matrix, but we will need 2 qubits to deal with that system. So in order to baby step you through the different sets of matrices we end up with, I wanted to start with the simpler case which we have in the project, which is a 2x2 matrix. And the 2x2 matrix is something which we can rewrite in terms of a Pauli X and a Pauli Z matrix. So let's quickly remind ourselves about the first part of the project. And this is what we have in the slides here for this week. We're actually going to look back at the Hamiltonian matrix which we have. So in general, when you set up a Hamiltonian matrix, you would have something like this. So where this represents the transition matrix element between a state 1 and a state 1. And this is the non-diagonal, which represents, in principle, a likelihood or probability of making a transition from a state 2 to a state 1. And we are going to expand things in terms of 2 basis states, because this is a 2x2 matrix. And let me quickly remind you of some of these technicalities by switching over to the whiteboard here. So instead of going through the slides, where you have essentially the same material, I wanted to switch over to the whiteboard so we can go through things a little bit step by step. So this is the beginning of the project, which we're going to deal with. So let me just bring that one back like this. So when we now, the kind of problem which we have a Hamiltonian, which is given by a 2x2 matrix. And these are the matrix elements which we have. It's a symmetric matrix, so H12 is equal to H21. And we have 2 computational basis states. And these basis states are 0, which we have previously defined as 1, 0. And then we have the other state, which is 0, 1. So these are the 2 computational basis states. And we have also split the Hamiltonian in terms of a so-called unperturbed part, plus one part which now contains a perturbation. Or we could say that this is the interaction matrix elements part. So H0 is defined so that H0 acting on 0 is actually an eigen, has as eigenstates this 0 and 1. So it gives us an eigenvalue epsilon 1 multiplied with this 0. And, sorry, this is 0. And then I have H0 acting on the state 1. That gives us an eigenvalue 1. And then we have the state 1 here. There was a 1 too much here. So this is often very common when you do quantum mechanical many-body physics, that you can define a basis which is an eigenbasis of parts of the Hamiltonian. And then you're hoping that the additional part can be seen as a perturbation. And that lays often the foundation for many-body methods like many-body perturbation theory, which is a widely used many-body theory. Now, what we can do now is to rewrite that matrix in terms of Pauli Z and Pauli X matrices. So what we are going to do then is just to define 2 new variables. We define this epsilon, which is epsilon 0 plus epsilon 1 divided by 2. And then I define a new variable, omega, which is simply epsilon 0 minus epsilon 1 divided by 2 here. So that means that I can actually rewrite, if you now look at the expressions here, I can rewrite this H0 in terms of these terms. So H0 acting on one of the states, I'm going to rewrite it in terms of epsilon times I. So this is now something which represents the specific matrix elements. So this is going to be given by plus an omega times a sigma z matrix. And from now on, I'm going to use the notation that sigma z is given by the letter z, uppercase letter. I define a sigma y, which is given by the uppercase letter y, and similarly a sigma x, which I rewrite as a x. So if I look at this H0, this is the following matrix. It's given by epsilon 0 here, 0, 0, and epsilon 1. So these are the matrix elements for epsilon 0. And you can see now that when you plug in the expressions for the matrix Z, which is the same as sigma Z here, with the 1, 0, 0, and minus 1, when you then use these definitions of the letters omega and epsilon, you will see that you get epsilon 0 and epsilon 1 here. So what I've done now is simply to rewrite H in terms, H0 in terms of two matrices, an identity matrix and the sigma Z matrix. Now what I can do next is to rewrite the interaction piece. So this HI is actually going to be given by matrix elements, which I'm going to call V11. So there could be some interaction matrix elements. These matrix elements here are the same, the non-diagonal ones. And then I have a V22 here. Now, again, I'm going to define some new constants. I will define a constant which I call for C, which is V11 plus V22 divided by 2. I have another constant, which I'm going to call for little omega of Z, which is the same as V11 minus V22 divided by 2 here. And finally, I have an omega X, which is equal to V12, which is again equal to V21. And then I can rewrite this H of I in terms of the following matrices. I have a C times this constant C times the identity matrix plus omega Z times the Pauli Z matrix. And then I have plus an omega X times the Pauli X matrix. And just to remind you quickly, so X is simply given by 0, 1, 1, 0. We are not going to need in the first part the Y matrix, but I just listed here for the sake of completeness. So this is minus I, and then 0 here. These matrices have some important properties. So we have an I squared equal obviously to I, and which is also equal to X times X, which is also equal to Y times Y, which is again equal to Z times Z. So these are some important properties with these matrices here. Now, what we are going to do now is to try to calculate the eigenvalues of this matrix. So this is a trivial matrix to diagonalize. It's a 2 by 2 matrix. It leads to simply a second order problem, which we know how to solve. So what we are going to do now is actually to overcomplicate considerably this 2 by 2 matrix problem. However, it's going to lay the basis for many of the things which we need when we are going to deal with quantum computing. So we have these two basis states now. And what we are going to do is actually to transform these basis states via rotations. So in a typical quantum computing environment, we are going now to change a state. So the state 0, we will have an input state 0, and we are going to change that one by a rotation around an axis, Rx, an angle theta. We are going to perform a new rotation here along the y-axis, and this is going to be given by an angle phi. So this theta and phi are just variables. And this ends in a new state, which I'm going to call psi here. So what it actually means is that I'm performing now a ansatz where I transform one of my computational basis states. So you could think of you preparing the system in the state 0. We know that the quantum mechanical system is in that specific state. And now we are going to make an ansatz for a more general state, a 1-qubit state. And this is in principle written as, so when you look at the graph here, it goes in this direction. But what it means is that we have an operation of y, of phi, and this is multiplied with a rotation of theta on the vector 0. So then we construct an ansatz, which will depend on these rotational matrices. Now, the reason why we do this is as follows. So if you think of the rotation operators, they are constructed via an exponentiation of the Pauli matrices, and it's common to use what's normally called the block sphere to represent any 1-qubit state. So let me quickly remind you of something which we discussed in the beginning of this semester. So the block sphere can represent an arbitrary 1-qubit state. So what we are doing now is to set up a general 1-qubit state. You can think of you preparing the system in the lowest lying state, 0. So you know that the system is in that state. And from that one, you now prepare a general 1-qubit state. So the block sphere can represent an arbitrary 1-qubit state through rotations. So let's try to make a drawing of it. So my drawing skills are not optimal here. So the angles theta and phi here are not the same as what we have in this example above here. In this example here, the angles phi and theta are just variables. So you could now think of having an ansatz for a state which depends on 2 variables. So we have the z-axis, we have the x-axis, and we have the y-axis. So if you think of a general vector, let's call this a vector A. So this has a projection on the z-axis, which is given by theta. And then we have a projection in the plane here, which now is given by an angle phi. And you've probably seen this thousands of times. Now we have a sphere like this. And this is also something which lives in the plane here. So as I said, my drawing skills are not optimal. If I now plot down here, this is the z-axis. This corresponds to 1, because we know that when z acts on the state 1, that gives us -1 multiplied with 1. So the computational basis states which we have chosen, the 0 and 1 states, they are eigenstates of the sigma z matrix. And here, so you could think of the south pole being represented by the computational basis state 1. And then you would have the computational basis state 0 up here, because we know that's the Pauli z matrix acting on 0 gives us back 0 here. So we say that the computational basis is an eigenbasis of these states. Sorry, of the Pauli z matrix. So every single qubit can then be represented by a set of visualized as a point on a 3-dimensional sphere. So let's just state that again. So every single qubit, and now we're thinking of 1-qubit system. Every qubit system can be visualized or can be represented, can be visualized as a point on a 3-dimensional sphere, on a 3-dim, and it's characterized by a radius which has value 1, with radius 1. So this is the coordinate r, and angles theta and phi. So these are the variables which are then used to represent a qubit. And the 0 and the 1 states, they are located on the north and south poles respectively. So when you apply a gate to a 1-qubit states, what that makes is it makes its corresponding point, you transform it from one surface point to another surface point on the sphere. And the qubit can reach any point on the sphere, which is defined by these spherical coordinates. And typically then, what you would say that a general state, if we now think of a general state psi here, that can be written as a cosine of theta half multiplied with 0 plus an e to I. It's actually not so difficult. This is just a relative phase, and that disappears when you perform a measurement, times a sine of theta divided by 2 multiplied with 1. That is a general state. And you can reach or perform this kind of operations with these so-called rotation matrices. And we defined this in the beginning of the semester. So let me just quickly remind you of these rotation matrices. So we just have everything ready. So the Rx of an angle theta is now given by e to the I of theta half x. So this is a rotation around the x-axis. And this rotational matrix takes the following explicit form. So when we now use the property of the exponential, and that the identity matrix squared is equal to 1, and the identity and the sigma x and sigma y, sigma z matrices squared are equal to their own values, equal to the identity matrix. So we can actually rewrite this one as a matrix, which looks like this. So it's a cosine of theta half. There is a minus I of sine theta half, and it's a minus I of sine of theta half, and then I have a cosine of theta half, which we again rewrite in the following way. So this is just a cosine, and you will see that in the code which we have here, multiplied with the identity matrix, minus I times sine of theta half, multiplied with the x matrix. We can do the same thing with the y matrix, rotation around the y-axis with an angle theta. And this matrix here is simply given by a cosine of theta half multiplied with the identity matrix and minus, and it has an I of sine of theta half multiplied with the y matrix. And similarly, what I also have is that the RC matrix is simply given by the following matrix. E of I is a minus I of theta half 0, 0 of e to the I of theta half. So these are important matrices because they are going to allow us to perform these rotations here. Okay, I see Karen already answered. I didn't see that one before now. So the ansatz means a trial solution. Thanks, Karen. Thanks for doing that. So when we now make this approximation, which you see here, this is just a ansatz or a trial solution based on rotations along the y and the x-axis. And these are operations which we can actually do with, for instance, laser fields being applied to a given system. So let's now continue. So we could have done a rotation around the z-axis if we wanted to, but let's now set this up as our ansatz. This is just one of tons of possibilities. And it's going to give us two variables, and these are called variational variables, because with such an ansatz, using the variational principle, which we discussed not last week, but the week before, and which lays the foundation for the VQE method, we can then set up an ansatz where we know that the energy which we will get, in case we have the exact wave function, is going to be given by such a transformation with the correct angles phi and theta, and we will get the exact energy. If not, if we don't have the exact wave function, then we will get a state which results in an energy which is larger than the exact energy we are targeting. Okay. So this was a little bit about the basic things which we're going to do now. So we are going to make these ansatz. And with that ansatz, we are now going to calculate the expectation value of the energy. So with this psi, which we have as a trial function, we will now evaluate the following quantity, which is now the expectation value of the Hamiltonian multiplied with this state here. So this is a quantity we want to calculate. And that means that we are going to calculate this quantity, which we call psi. And then we have this variables. So let's now go back and look at the Hamiltonian, which we have. So the Hamiltonian, which we have, is rewritten in terms of these Pauli Z and Pauli X matrices and the identity matrix. So we can rewrite this in the following way. So we would now have these variables, epsilon plus this constant C multiplied with the identity matrix, plus this omega plus this parameter omega Z multiplied with this C matrix, plus this omega X multiplied with the Pauli X matrix, and then we have to calculate this corresponding value here. So the thing which we're going to do now is we can do this either by paper and pencil, or we can just set up a simple program where we define the Pauli X, the Pauli Z, the identity matrix, and then we perform these rotations. And then we see what kind of value we get. And from the variational principle, so let's call this one for E trial or ET. So this is a trial energy with that specific ansatz. So we should put a T here to indicate that this is a trial state. It's not the exact state. So this is our psi of T. And then from the variational principle, we know that the lowest lying state what we have then is that this ET is larger or equal than epsilon 0, which is the exact lowest state. Okay, so with that, we can now simply just calculate and see what we get. So let's go back to the Jupyter notebook and set these things up. So essentially what you will see now is me just trying to implement these solutions which we have. And I've redefined these parameters as we did. And I also put in specific values for these parameters. So I took this E1 to 0, E2 to 4. These are just choices which I made. And you could even think of letting your Hamiltonian depend on a parameter lambda, as we have in the project. So here, I'm just going to put in a lambda equal to 1, which means that that is the fully interacting case. So if you look at the case which we have, this is now me setting up the Hamiltonian matrix with these parameters. I have this non-diagonal, which is 0.2, the diagonal, which is 3. I'm setting it up here. I calculate the eigenvalues, and I write out the lowest lying eigenvalues. So this is the value which I'm targeting and which we want. So the next thing which I do now is simply to rewrite everything in terms of the Pauli X and the Pauli Z matrices. So I'm just plugging in these expressions which we set up. And if we diagonalize, then we should just get the same result. There shouldn't be, unless we have punched in things wrongly. So you can see now that when we rewrite it in terms of the identity matrix and the Pauli matrix X and Y and Z, then we end up with the same eigenvalue as before. So if you now run it, you will see now that we have exactly the same value as it should be. So the next thing which we're going to do now is to implement this variational quantum eigenvalue solver or quantum eigensolver. And with the quantum eigensolver means that we have an ansatz. And the ansatz which we are going to do now is simply to repeat a little bit of what we said. For one qubit system, we can reach every point on the Bloch sphere with a rotation about the x-axis and the y-axis. This is just one way of doing that. And what we end up with then, with two variables, theta and phi, so these are just chosen variables, we now start with a state in state 0, the computational basis state, and then we perform a transformation. So we will still be on the Bloch sphere, but we will not be on the North Pole or the South Pole. And then we can produce multiple ansatzes for this new state in terms of these angles, theta and phi. And with these ansatzes, you can in turn calculate the expectation value of the Hamiltonian. So what we end up with then is now to plug in these expressions and simply calculate the expectation value and then see what that gives us. So if we now also, what I've done here simply to list the matrices. So what I have here is now two randomly chosen values for the angles theta and the angle phi, nothing particular. And then I set up my Rx and Ry. I have the basis 0, so everything is hand-coded here. And in a way, this is how you could proceed when you get started with a project. So I'm setting up these equations here as a kind of a guide for how to get started with project number 1, or the project itself. And that means that when we do this basis state, I can compute a new basis, which is now simply the multiplication of these states which we have here. So since these are matrices, I should actually rewrite it like this. So let me just bring that back here. So I'm just performing this matrix multiplications with the Rx, Ry, and then I multiply that with the basis. And then finally, what I end up with here is now to calculate the energy, which is now the product of this transposed state, which is the one which we have here. And this is multiplied with the Hamiltonian matrix, and it's multiplied with the basis which we have here. So if I run this, oops, just a moment here. So this should be times t here. Okay, so let me just redo it here. So if I set up my new basis and then I calculate the eigenvalues, that should be 1.3, and then I have an imaginary component. And this is actually not a very impressive result if you think of the result which we wanted, which is 0.9. Now, what you could do next, and this is actually what you end up doing, is to now set up a series of angles. In principle, you could now set up random values for these angles. So I'm going to set up an array which contains angles from 0 to pi in steps of 10. And now I compute this variable theta and phi, and I perform my rotations. And when I perform my rotations here, the next thing which I get is the new basis. And with the new basis, I can then compute the expectation value of the Hamiltonian. And what I'm doing then is to calculate the difference between the exact result and the one which I get when I compute this expectation value with these basis states which I have. Now, with that, I can then list the differences, and then simply here, without doing any kind of intelligent minimization, I pick the smallest difference. So what you will see here is not the optimal way of doing it, but it's actually the way you would do it. So I've chosen these different angles, And I found now that for a specific choice of these angles, I have the minimum difference, which is actually pretty small. So I'm getting close to the exact solution. Clearly, and this is for you in the project to look at, this is not the best way of proceeding. Because rather what you should do now is to, with that specific ansatz which we have, if we go back to the expression, this one, you should now take the derivative of the expectation value of the energy in terms of phi and theta. That means that you would evaluate the gradient. And with a gradient, you can then use a gradient descent method to find the optimal parameters theta and phi, where the gradient vanishes. So the way this is normally done is that you have an optimization problem where you now find the optimal values of theta and phi by using a standard gradient descent method. That means that you need to have the derivative of this quantity here with respect to the angles theta and phi. So one thing you could add here, and this is one of the things you have to do in the project, is to add a gradient descent optimization and find the optimal values. And that will give you the best energy for that specific system. Now, when you do this, you can do this obviously using Qiskit, which has this baked in already. But I would recommend that you actually go through the basic steps, which I put up here, and try to run through the details and see whether your gradient descent actually gives you this optimal expectation value, which should then be equal to the state which we get up here, 0.9 something, with those chosen parameters. So this is the first step in the project, and you can actually look at these examples which I put up here and try to run through these calculations. And the reason why we do this, which will be obvious after the small break which we take, is that rewriting the Hamiltonians in terms of this X, Y, and Z gates is going to allow us to set up measurements. Now, keep in mind, and this is something which becomes important after the break, is that the computational basis which we have chosen, 0 and 1, these are eigenstates of sigma z. That means that when we want to perform a measurement, when sigma z acts on a linear combination of these 0 and 1 states, we get an explicit number if we now measure on state 0 or state 1. Sigma x, or the X matrix, on the other hand, does not have the computational basis as an eigenbasis. So that means that we would need to transform the Pauli X matrix in terms of something which can be expressed in terms of Pauli C matrices. And that's something which we're going to study after the break. So what we have done here is not the smartest way of doing things. So you can do it, but this is not the way you would proceed if you're setting up quantum gates and circuits in order to perform measurements. So let's take a small break now, and feel free to ask questions in the meantime. So to recapitulate what we discussed before the break, what we are doing now is to make an ansatz or trial wave function for the 1-qubit state, which lives on the Bloch sphere. And this is now based on a rotation around an arbitrary angle theta along the x-axis and an arbitrary angle phi along the y-axis. So this is a general representation of a qubit state. And we are going to diagonalize this 2-by-2 problem using a 1-qubit basis. And in this specific case, we can actually use the computational basis 0, qubit 0, and the computational basis 1, which now represents qubit 1. And with these two states as a computational basis, we can then set up the Hamiltonian matrix and diagonalize exactly. Or alternatively, we can use the variational quantum eigensolver. And if you go back to the lectures from week 8, which we had, so this specific week here, which was March 13th to 17th, I have added a lot of material on the variational quantum eigensolver. So if you scroll down on these slides after the discussions of this Lipkin model, you will find a discussion at the end here of these slides after all these kind of mathematical transformations of the matrices. And after a short discussion of mean field solution, you will find a discussion of the variational quantum eigensolver. And also a discussion on how you would implement it. And as you can see, what you would typically do now is to prepare the variational state as a function of this angle theta, or a set of angles. You would measure this circuit in various bases and send these measurements to a classical computer. And the classical computer post-processes the measurement data to compute the expectation value. And now what we are going to do is to run everything on a classical computer, which means that we are going to set up the ansatz, we are going to calculate the measurements, and with these measurements, we are going to find this expectation value, and we are going to optimize these parameters. So that means that we need some kind of gradient descent here. And in our particular case, we can then actually find the gradients easily, or we may need some labor. So if we go back to what we have this specific week here, so this should be not that week, but this one. So when we implement the VQE in this simple case, the first example which we went through was just a very brute force way of doing it, where we simply calculated the energy and took the energy difference based on a chosen set of angles, theta and phi, for performing the rotation along the x-axis and the y-axis. And then we simply calculated the difference and we found the minimum value. This is not the way you would do it. The way you would do it is to calculate the gradient of this energy as a function of the parameters theta and phi and optimize the gradient. That means driving the gradient to zero. And that gives you the optimal parameters. When you then have the optimal parameters, that's when you would launch a series of measurements with these optimal parameters. And then the final expectation value, which you would list, would be an average of all the measurements you have made. That is the basic recipes for finding the eigen states of the and eigenvalues of this system. Now, what you've seen here is the basic approach to how you get started with a project. But I haven't given you the gradient descent algorithm. And this is something which you have to sort out. And for those of you who've taken physics SDK, the machine learning course, you know exactly how to do this. However, what we have done here is not the best way. It's actually not the way you would perform this type of operations. So the above approach means that we are actually setting up several matrix and matrix vector multiplications. And the more complicated the systems, the larger the matrices. And many of these matrices, which will then involve C0 gates, etc., for more than 1 qubit, they're going to be large and sparse matrices. So that means that the approach which you've seen here function as a kind of pedagogical approach for the 1 qubit case, for a 2x2 matrix, but it is not very efficient for a many qubit case. That means that from a computational point of view, performing this matrix and matrix vector multiplications is not the best way of setting it up. But there is more to that. There's more to the picture than meets the eye here. One of the reasons is that when you want to perform a physical realization here and perform measurements, you would like to perform measurements using operators which are relevant for the computational basis. And we know that the sigma z, or either written in terms of the Pauli Z matrix or just as an uppercase letter Z, when that acts on the state 0, we can then show, and we have seen that before, that this is an eigenstate of the sigma Z matrix. Similarly, with the other computational basis state 1, this is also an eigenstate of the sigma Z matrix with eigenvalue -1. If, on the other hand, I use the sigma X matrix, this eigenbasis which I have is not an eigenbasis of the sigma X matrix. And this applies also to the sigma Y matrix, because the sigma Y and the sigma X matrices, they are almost the same, except for a minus sign and the imaginary number I. So that means that if I have a Hamiltonian like the one which we have, which we go up a little bit again, we have actually a sigma X matrix here, which gives the link to the non-diagonal matrix element. And this is a quantity we need to rewrite. So rewriting that quantity is something which is actually pretty straightforward. So we can actually use the so-called Hadamard matrix. And if we use the Hadamard matrix, what we end up with then is a matrix H times Z times H, which is the same as the Pauli X matrix. And this is the replacement which we are going to make in the Hamiltonian in order to set up the calculations here. If you have a Pauli Y matrix, this is a little bit more complicated because that's going to be given by the phase combination of the phase matrix and the Hadamard matrix. So remember, this H is not the Hamiltonian, but it's actually the Hadamard matrix. So that means that you can rewrite your Hamiltonian, you replace the X matrix in terms of a Hadamard matrix acting on the state which we have here. So we perform the rotations, and then at the end we have actually a Hadamard matrix. So it means that the new state which we have will now be given by a slightly different circuit than the one which we had before. So we need actually to set up the state psi here, but we're also going to have this state psi multiplied with a Hadamard matrix. And that is an additional calculation which we need to do. And remember now again that this state psi is a linear combination of the computational basis states 0 and 1. So when I then act with Z on this linear combination, I just get a constant times the states 0 and 1. So acting also on with the Hadamard matrix on that state gives simply a linear combination of those states. So let me go back to the whiteboard and try to stress this a little bit more so that you see what we actually have to implement computationally. So the Hadamard matrix does not include any new parameters, so which is very beneficial. So if we now look at the operations which we need to add in order to be able to perform a physical experiment. So the experiments, the way we measure it, means that we would have to apply an operator which projects out one of these specific states. So if you now think back to the states which we had, 0 and 1. So what we have done is to produce a new state, which now depends on these rotations with the randomly selected angles. We don't know which one are the relevant ones. And this is acting on the state 0. We could also prepare the system in a state 1. Normally, we would prepare the system in a specific state. Now, if you now remember the action of the Hadamard matrix on the state 0, this is the same as us taking a 1 over square root of 2, and then we have 1, 1, 1, minus 1. And this is then multiplied with the state 1, 0 here. And if we now look at that calculation here, what we get is a 1 over square root of 2. And then we have a 1 here. And what we also get now is that we get a mixture of the one state. So that means that we have a mixture of a linear combination of, we say it's in a superposition of the state 1 and 0. If I act on the state 1 with the Hadamard matrix, then this is given by 1 or 2 of 0 minus 1. So we went through some of these operations in the beginning of the semester. When we now have performed an operation on Ry with Ry and Rx of theta, what we get then when we act on 0 This is going to give us a linear combination, and I'm going to write this as a coefficient alpha, which depends on phi, and a coefficient beta, which depends on theta, and it's going to have a combination 0, and then it's going to be a coefficient delta, which depends on phi, multiplied with a coefficient gamma, which depends on theta, of 1 here. So these are the different cosine and sine operations, which I just have spelled out in terms of these functions, which I have left undefined. So remember now that the rotation around the x-axis is given by a cosine theta minus an I times a sine theta multiplied with the Pauli X matrix. And then I repeat the operation with the Ry matrix, and that gives us a linear combination of these specific states. So when we have that, then we apply the Hadamard matrix again. And with the Hadamard matrix, we can then now perform a measurement of the specific state which we are interested in. So just to remind you, the sigma X matrix is given by, if I now take the Hadamard matrix and multiply that with the Pauli Z matrix, that means that we are performing this operation here. And this is multiplied with 1 over square root of 2, 1, 1, 1 minus 1. And that is going to give us simply 1 over 2, and then we're going to get 0, 2, 2, and 0. This is the sigma Z matrix, this is the Hadamard matrix, and this is a Hadamard matrix. And this is simply given by 0, 1, 1, 0, which is the Pauli X matrix. So this is the way we would typically rewrite the Hamiltonian then. So our Hamiltonian now is given by, so let's put an operator sign here. So we have a constant, and I'm just going to call this constant for alpha. We have the identity matrix. We have a new constant beta, which is given by a sigma Z matrix. And then we have the other constant gamma, which is now given by the sigma X matrix. So which we again rewrite as an alpha of I plus a beta of Z plus a gamma times the Hadamard matrix multiplied with the Z matrix and multiplied with the Hadamard matrix. And when we then calculate the expectation value, what we are going to do now is to simply calculate this quantity here, where psi is a function of phi and theta. And we can write this as a phi trial. I'm just going to write it as a psi of t of the Hamiltonian h. So h with a hat to indicate that this is different from the Hadamard matrix. So what we end up with is a constant alpha. And then I have psi of t multiplied with the identity matrix of psi of t. And this is an obvious quantity to calculate. This is just psi of t. So this is pretty trivial. And then we have a beta multiplied with psi of t. And then I have the Pauli Z matrix. And that is going to pick out the right projection of the linear combinations of 0 and 1, plus the final one, which is a gamma. And then I have a state psi of t multiplied with the Hadamard matrix. And then I have the Z matrix, and I have the Hadamard matrix and psi of t. So what I would need to do now is the following when we look at measurements here. So the first term, let's call this term 1, and then we have term 2, and then we have term 3. So for term 1, that is pretty straightforward. We don't need to set it up because just the identity matrix. If we now look at the term 2 here, that is also a pretty trivial term because we are just calculating the expectation value of the Z matrix. So what we will do then, when we now set up the term 2 here, that is simply going to be given by the state 0. So this is a kind of circuit which you would set up. And I have my state Rx with an angle theta. I perform a new operation. So that's the next one, or y of phi. And then I'm going to put a bar here to indicate that this is where it stops. And then I perform a measurement. And this is the output. So this is normally written like this. So this is our measurement. And if we go back to the lectures which we had some time ago, then we know exactly how to compute the measurement. And when we do that, we can repeat this again and again and again. This is actually what we would be doing experimentally as well. And then the final observable is actually the average of all these expectation values. Then for the part 3 here, what we need then is now a similar operation as the one we had previously, but now we need to set up a circuit where we calculate Rx, and I'm just skipping the angle here. I calculate Ry. But then my next stage here is actually to perform a Hadamard transformation of this state. And then finally, I have a measurement. And the measurement is now done by this sigma z operator. So this is our z operator, which performs the final measurement on the state. So this is the graphical way you would set it up. From a computational point of view, the only thing you need to set up is simply the additional operation of a Hadamard matrix. So if you look at the codes which I put up in the beginning, the only thing you actually need to do is to move on to a set of Hadamard matrices which act on the Z matrix. And that's it. So for the 1-qubit state and part A and B of the project, you should have essentially all things which are needed. And the only thing you would need to add would be doing an optimization over the angles theta and phi, find the gradients and find the optimal parameters. And when you have the optimal parameters, you would simply perform a series of measurements and then calculate the average value of this.
Could you scroll a bit up on the whiteboard? I was just...
Say it again.
Could you scroll it just a bit up on the whiteboard?
Yeah. Say stop.
Yeah, just a little bit more, because you wrote the acting of you act with the rotation matrices on the basis state 0, and you rewrite it in terms of alpha, beta, delta, and gamma.
Yeah.
I lost you for a second on the why did we rewrote it with the delta and gamma acting on basis state 1.
No, because if you when you perform this transformation here, you get a linear combinations of zeros and ones.
Okay, yeah.
And what I did now was I didn't specify if you go up again, so I just left it total in a very general way. If you look back at the matrices which you have here, so what you have is a matrix, the Rx here. If you look at the definition of the Rx, so let me just write it down here so you can see it clearly. It's a little bit noisy in your background. If you just
I forgot to.
You just could unmute yourself because So if you look at the Rx of theta acting on this computational basis state, what we get then is the following. So we have a cosine of theta half with the identity matrix minus an I of a sine of theta half and multiplied with the sigma x matrix, and this is acting on 0. So what happens then is that I obviously get cosine of theta half multiplied with 0. So the identity matrix just gives us back 0. But then we know that x, when that acts on 0, that gives us the state 1 here. So what I get then is minus, I have a linear combination of these states, sine theta of 1 here. And this is something which I just wrote out in terms of a dependence on the angle theta and a dependence on the angle on the on cosine theta and sine theta here. And when I then, so this would be that specific operation. And when I act on this state, so let me just take that one away. So the next operation is an Ry of phi, which is given by a cosine of phi half with the identity matrix minus an I of sine of theta half multiplied with the Y matrix. When this now acts on these states, what I would get then is obviously a cosine of I multiplied with cosine theta of 0, which is obviously given by, so what I'm going to get then is when I take Ry of phi times an Rx of theta acting on the state 0, which I prepared from the beginning. What I would get then is now a cosine of theta half multiplied with a cosine of phi half. And this has now the identity matrix. And this is multiplied with the state 0. So that's the first term. Then I have a new term here, which is going to give me, if I look at the state which I ended up with, I'm going to get a minus a cosine of theta half, which now contains a, it's a phi half multiplied with the identity matrix. And this is now also multiplied with I of sine of theta half multiplied with 1. So that's the two first terms. And this simply gives us back the state 1 multiplied with a cosine phi half and a sine theta half. And finally, what I get is now the next term here, which is going to be given by a plus. And now I'm going to have a, sorry, not that one. I'm going to get a minus an I of sine, and now I have a sine phi half multiplied with the Pauli Y matrix. And this is multiplied with a cosine of theta half of 0. And then I have a sinus theta half and sinus phi half. So this should be a phi actually. So I get the minus I, that's plus, but then I get a minus. So I get a sine of theta half multiplied with a sine of phi half multiplied with a matrix Y, and then multiplied with a vector 1 here. So that gives us, when we now sum up here, it's going to give us the following. So I'm going to get a cosine theta half multiplied a cosine phi half, and this is multiplied with 0. I get a minus cosine phi half times a I of sine theta half, and this is multiplied with 1. And then I know that when I act with the Y matrix on a state 0, that gives me simply I. So I get, and I'm going to get the state 1. So I get plus sine phi half cosine theta half, and this is multiplied with 1. And then I get, in addition, minus, and I'm going to get sine, and this is going to have an I sine theta half, sine phi half, multiplied with 0. And these are the functions which I put up, this generic function alpha of theta, gamma of beta, etc., etc. So this is actually what you would get when you perform these operations. I hope that helped a little bit in seeing what's going on.
that about a lot. Actually, you just had to tell me that it's because of the rotations that we all of a sudden just get the other basis state in the combination.
Yeah. Now, the thing we need now to do is to move the 2 qubits. So let's go back to the slides and just remind ourselves of the next part of the project, which now deals with a 2-qubit system. And the 2-qubit system deserves some attention now because we still want to rewrite everything in terms of Pauli X and Pauli Y and Pauli Z matrices. So if we now look at the system which we have for the 2-qubit system in the VQE, so it's very much the same procedure, except that now we have to enlarge the matrix from a 2x2 matrix to a 4x4 matrix. So in this particular case, we are now taking the same computational basis states, 1 and 0, for the single qubit cases. And then we construct now a new computational basis. This could also have been the Bell states if we want to. But we are going to define this as the computational basis which we have. And with that computational basis, what we can do then is now to define a new Hamiltonian, H0, which has these states as an eigenbasis. So we are then simply defining these as eigenstates of H0. And later we are going to see that we can actually rewrite this in terms of this H0 in terms of different Pauli matrices. And then we define now a interacting part of the Hamiltonian, which just has a constant here, and the product of 2 Pauli X matrices and a product of 2 Pauli Z matrices. And that means that we get the following Hamiltonian in our case here. So what we want now is actually to be able to rewrite this Hamiltonian here, which you see when we make measurements. So one brute force way of doing this is again to produce the same ansatz as we did before. So we can perform a rotation in the along the X and the Y axis for system A and system B, or we can just take system A, which is being rotated, and perform an ansatz then, which is a 0-0 state, which then would be given in terms of a transformed qubit in the A system or qubit in the B system, or transform both. The next step is then to perform the measurements. So clearly we can again just perform this matrix operations times a vector. There's nothing which hinders us from doing that, but that's not the way we will do the measurements. So when we're going to do the measurements now, we need to translate like the sigma X matrices in terms of Pauli Z matrices. So there are a set of ways of doing this. And so let's just set this up. After we've done with that, there is a set of notes here on how to use Qiskit to actually find the eigenvalues of these systems using the VQE. This is something which we will discuss after the Easter break, but I invite you to take a look at these topics before the Easter break, because we will not meet before April the 17th again, since April the 10th is a holiday in Norway. So let's go back to the whiteboard and try to set up these 2-qubit systems and see how we have to rewrite the different matrix elements which make up the Hamiltonian. So the Hamiltonian which we have here is just an example Hamiltonian where I just took the tensor product of 2 Pauli X and 2 Pauli Z matrices. But let's go back to the whiteboard and set up these kind of calculational details which we need to have in order to rewrite everything. Oops, it should be coming up. Here we are. Okay. So the 2-qubit case. Let's take that one. So suppose now that we have only a Z matrix which acts on one of the qubit systems. So one of the matrices which we would need to deal with now is a matrix like this. So this is a 2x2 matrix, identity matrix, and this is obviously a 2x2 matrix. And if I set this up, this is going to be given by 1, 1, minus 1, minus 1, and then I have zeros for the rest. So this is a typical matrix which appears in the Lipkin Hamiltonian. So in the Lipkin Hamiltonian, what we have there is a part which is proportional. So it runs over all the particles which we have. And then it has a sigma of I, and it contains then, so the sigma I is just a quantum number, which can be plus minus a half. And this contains now the Pauli Z matrix, Z of I. And that acts only 1 qubit at a time. Only on 1 qubit at a time. This means that we actually need to rewrite that operation here in terms of the Pauli Z matrix, which acts on one of the qubits, and then multiply with the identity matrix, because we don't act on the other qubit. So that means that we need now to be a little bit careful with the way we are setting up these kind of operations here. So the standard recipe by which we do this now is simply to perform a set of unitary transformations, where we now find the way these matrices are going to act on a specific system. So in general, what we are going to have now, when we do a measurement, when doing a measurement, we need the following. So this is the following expression. And what we have is a unitary transformation acting on this Z times I. So it acts on one of the qubits. And then we perform a new unitary transformation here. So this is actually a matrix which will map to a space with the same eigenvalues of plus and minus 1 as we have for the Pauli Z matrices. So we can apply a similar trick as we did in the 1 qubit case and apply this set of transformations for the Z matrix, for Z times I. This is actually a pretty trivial operation. And in this case, what we end up with is that this matrix U is simply given by a unitary or an identity matrix of dimensionality 2 times 2, cross-producted with a tensor product with a unitary matrix of dimensionality 2 times 2. Not unitary, but an identity matrix. So for this specific operation here, where we already have everything as a Z matrix, we don't need to proceed with more than that. Now, however, there are many other types of matrices which we are going to encounter. So when we look at the Lipkin model, one of the cases which we had is an X of I times an X of J, if we look at the Hamiltonian. And then we have a Y of I times a Y of J. And this is a term which appears in front of the interaction piece. So what we need now is to be a little bit more careful. And we have to set up these operations in a slightly different way. So if I take the X times X matrix, actually what I need then, and this is a controlled knot matrix. So let me bring down, so I'm going to rewrite this as an X times X, and this is a Y times Y. if I also have a C times Z, so what this stands for is X times X. This is a Y cross product with Y. Remember, these are 2x2 matrices. And now we want to go to a two-qubit system. So that means that they have to be 4x4 matrices. And then we have to perform the tensor product. So C times Z is actually something which corresponds to C tensor product with Z. So when we now want to perform a measurement then for C cross product C, then this matrix which we're going to have, this unitary matrix, or the operator, which makes a transformation for us, is going to be the so-called controlled knot 1-0 matrix. So this is a CX is a controlled knot matrix. And this controlled knot matrix, let me just remind you of what that one looks like. So this CX10 is a matrix which looks like this. And there are tons of these matrices, 1, 0, 0. 0, 0, 0, 1, and then I have 0, 0, 1, 0, and then I have 0, 1, 0, 0, if I got this right here. The next matrix which we need to look at and transform in terms of a sigma Z matrix is the XX matrix. So X times X. This has now a unitary transformation as U, which is equal to the following matrix. So I'm going to have this CX10, which is the same matrix which we had before. And in this particular case, what we're going to have then is this matrix multiplied with a tensor product of two Hadamard matrices. So I'm just listing up all these kind of alternatives which we have, because we would have to implement them. So this is going to give us X times X. When I now perform these operations, I will actually get something which I can rewrite in terms of the Z matrix and with this kind of transformed matrices here. So that means that when I perform that transformation, I will then get something for the XX, which is actually going to be equal to this U, which we have here, that one. And inside here, I'm going to have a Z times a Z and multiplied with the same U, which you see here. So this is the way I would have to transform an X times X matrix in order to get a set of Z matrices. And then I have a Y times Y, and this is the last thing we're going to set up. But we have tons of these relations here. But for the project, what we need is actually the Y times Y. And in this case, it has a unitary operator, which is given by the control knot matrix. And then I have a Hadamard matrix multiplied with the phase matrix. And this is a tensor product of H times S, like this. So remember now that everything which is in here is a 2x2 matrix. And this matrix S is a matrix which looks like this, has 1, it has I, and 0 here. This is normally called the phase matrix. So we would need now to change, when we want to perform measurements, we have to change the X times X and the Y times Y in terms of these transformations, so that we can actually rewrite everything in terms of us calculating expectation values with C matrices only. And when we have that, then we can perform the measurements. This is going to stop today's lecture, because I see we are over the hour here. And coming back to the slides, just to give you that as a quick message here. So when you look at the slides here, the thing you would need to do in this specific case, so here you already have the sigma Z and sigma Z matrices, so they are trivial to represent, but you would have to transform the sigma X tensor product sigma X in terms of sigma Z matrices. And then you can perform the measurements as we did with the 1-qubit case. And it obviously gets more complicated when we now have more and more qubits, and you need more and more complicated gates, because every such operation represents a specific gate. And clearly, how long we can run these simulations depends on the physical system which we are implementing these operations on. But this should be the basics of this, the first part of the project. And when we move to the Lipkin model, the thing we need to plug in then is actually the Y times Y matrix. I invite you also over the break to take a look at the Qiskit notes, which have been developed by Stian, because that makes life much simpler. But if you wish to write your own code for these operations, feel free to do that. And what I plugged in here in the very beginning is actually an example on how you can write your own code for the single qubit case. And this is something you can expand to the 2-qubit case. And in our case, for the first part of the Lipkin model, when we have a total spin equal to 1, that's going to correspond to a 2-qubit case. Okay, so I'm going to stop here today. And I'm going to stop the recording. And then I just wish